Hello friends, I am Professor D.G. Trivedi. I am going to take your second lecture in method of images. In method of images, we have discussed actually the problem of classic image problem. What was that problem? You see this figure. There was a conducting sphere and there was a conducting plane kept at xy plane at z is equal to 0 and point charge q was placed at a distance d above this conducting plane. And we could find out the potential in the region z is greater than 0. That means upper part of this conducting plane we could find out. And for that we have taken the analogous problem like this. We have taken only 2-point charge plus q and minus q and no conducting plane. They are kept at a distance plus d and minus d on a z-axis. And the potential for this configuration was calculated like this. It was found out by this one. And that potential is satisfying the boundary conditions of our original problem, and hence if z is greater than 0, this potential was there. So this is the things we have already studied. Now we want to see that why that was potential was there. Here we have seen that because of this point charge q plus there is a negative charge was induced on a conducting surface. This negative charge was coming to the surface of this conducting plane, and that negative charge was distributed, and sigma, which is a function of xy, that we have find out in this solutions. And then the total charge was minus q was induced for a conducting plane that we have seen actually. Now what will be the force exerting between these two systems? Here in this system, what will be the force will be there plus q charge and the induced charge, and here what will be the force, that is analogous problem force will be, we will find out. But here because of this positive charge and negative charge, there will be definitely force of attraction is going to be there. Since the potential in the vicinity of the q is the same in analogous problem, one way with plus q and minus q but no conductor, so also the field and therefore the force also will be analogous for both the system. Why this is going to be happen? We have already find out the potential in the both the system was identical. What is the electric field? Electric field is nothing but the gradient of potential. Hence, in both the system, the electric field is also same in upper regions will be there. In lower regions here, the electric field is going to be 0. Here in the lower regions, because the charge symmetry, the electric field is also symmetrical. So we can see that in both the system, in upper region of our interest z is greater than 0, the potential is same, the electric field is going to be the same, and what is the force is equal to q into E. So the force is also going to be the same in both the system will be there. So to find out the force between this charge q and the induced charge on a conducting plane, we'll find out what will be the force between these two charges will be there. This force is you can find out using the Coulomb's law. What is the Coulomb's law? The force between the two charges is equal to k or 1 upon 4 pi epsilon 0 q1 q2 upon r square, where r square is nothing but the distance between these two charges. So distance between these two charges plus q and minus q is equal to d plus d, that is equal to 2d will be there. So d square means 4d square will be there, and hence the force can be given by q1 q2, that is going to be both the magnitude are going to be the same. So q square, one of the charge is negative, so minus sign, and 1 upon 4 pi epsilon 0 q square upon 2d whole square, that is going to be 4d square, that is going to be there, and the direction of the force will be in negative z direction, because that will be the force of attraction is going to be acting between these two charges, because one is positive and induced charge is going to be negative. Now you see that we have seen that in both the system the potential was same, electric field was same, the force was same. So we may be careless that everything may be the same, but it is not true. Energy is not going to be same in both the cases. So you can read here beware, it is easy to get carried away and assume that everything is same in the two problems. Energy, however, is not the same. With the 2-point charges and a conductor, equation 2.42 gives what is the energy? Sorry, W is equal to minus 1 upon 4 pi epsilon 0 q square upon d. But for a single charge and a conducting plane, the energy is half of this. W is equal to minus 1 upon 4 pi epsilon 0 q square upon 4d. Here it was 2d. So this is again divided by 2. So the energy becomes half in this case. So single charge and conducting plane energy is half of this system where there are 2-point charge and no conducting plane. Why this energy is going to be half? Everything was same, potential, electric field and force were same in the two systems, but the energy is half. What is the reasons? Because the energy is calculated from this formula. W is equal to 1 half epsilon 0, the integration of volume integration of electric field square d tau. So using this formula, we calculate the energy. In a first case, in the first case, both the upper region z is greater than 0 and lower region z is less than 0 contribute, and by symmetry they contribute equally. That means if there are 2-point charges and no conducting plane, there is an electric field in upper region also and as well as in a lower region also, z is less than 0, and both the electric field are almost identical, and hence they contribute for this integration and energy will be twice in that system. But in another system, when there is only point charge and no conducting plane, the energy is going to be half, because only upper regions there is the electric field is going to be exist and lower regions the electric field is going to be 0, and that's why it is going to be half. Of course, one could also determine the energy by calculating work required to bring a charge q in from infinity. So, if we bring a 1 coulomb positive charge from infinity to a distance d, the amount of work done is called the energy or potential. That way the definition was given. So, if you are bringing this q charge plus q charge from infinity to a distance d on z axis, the amount of work done you calculate, and that will be the energy stored with that charge will be there. Now, what is the force between this? How to calculate this work done? Work done for a variable force, because the force is going to be changing as the distance q1 q2 upon r square. R is going to be changes, and hence we can say that the force is variable, and for the variable force this formula will be utilized to calculate the amount of work done. W is equal to integration from infinity to a distance d. We are bringing a charge q at a distance d, f dot dl. So using this formula, you can find out the work done, or you can find out the energy related with the charges. Now what will the force is equal to? Already we have seen 1 upon 4 pi epsilon 0 q1 q2, that means q square upon, and variable d is going to be z here. So 4z square dz, this integration will give you the amount of work done to bringing a point charge from infinite distance to a distance d. Now, in this integrand, q square upon 4 is a constant which can be taken outside and remains the integration of 1 upon z square dz. What is the integration of 1 upon z square dz? Integration of this one is nothing but minus 1 upon z. So that we can substitute minus 1 upon z here, and integration is having a limit from lower limit is infinity to a distance d. Substituting from higher limit to the lower limit, we will get that if d is equal to z is equal to d, we can substitute here, and z is equal to infinity, this quantity is going to be 0. So finally, the amount of work done is equal to minus 1 upon 4 pi epsilon 0 q square upon 4d. As I move q toward the conductor, I do work only on q. If It is true that induced charge is moving in over the conductor, but this costs me nothing since the whole conductor is kept at potential 0. That is one of the boundary conditions given. That means conducting plate was grounded. So even if the charge is induced and that may be moving on a conducting plane, that amount of work done because of that moving charge is going to be 0 because that is kept at a potential 0. So no work will be done. Only work is this, that is bringing from infinite distance to a distance d. By contrast, if I simultaneously bring 2 point charges plus q at a distance d and minus q at a distance minus d on second configuration with no conductor, I do work on both of them and the total energy is twice that of the previous case. Now, we can study the other image problem also, the similar manner. What is this other image problems? Here in a previous case, we have taken only single point charge here. In this region of interest, there was only single point charge. Instead of that, in this region of interest, there may be a point charge distribution is going to be there. Discrete point charge distribution, Q1, Q2, Q3, Q4, etc. is going to be there. So we can image here in this lower regions. Also there is a charge Q1, Q2, Q3, just exactly the mirror image of this charge distribution we can think about here. And they are also at the same distance like this. Here there is a positive charge and here there is a image charge is going to be placed at the same distance. That means this is a mirror image. And similar way, instead of one charge, if there are more than one charge is also going to be there, charge distribution is also there, then also we can think about the mirror image and hence and we can calculate the potential for both the system and it is found to be identical using the principle of superposition. That is the reasons why this method is known as method of images. Remember that the image charges have the opposite sign. That means upper charges is positive, then the lower charges will be the negative. Or the charges may be a mix. Some of the charges Q1, Q2, Q3, etc. may be positive, and instead in that one combination, some of the charges may be negative. But whatever the charge distribution you think in uh, other regions, that should be completely opposite charges should be there. And this gives the guarantee that on xy plane at z is equal to 0, the potential will be 0 everywhere. There are also some exotic problems that can be handled in a similar fashion. The nicest of this is the following. So we are going to study some another problem. Next problem is going to be this. That problem is given 3.2. A point charge q is situated at a distance a from center of a grounded conducting sphere of radius capital R. So we think about this is a grounded conducting sphere and it is potential is kept 0 because it is grounded. So this is one region inside the sphere, there is another region outside the sphere will be there, and from the center of this one a point charge q is kept outside the regions at a distance a from this one, and you are asked to find out the potential in this region, that is outside the sphere. Inside the sphere the potential is going to be 0, so no need to calculate that one. Only outside there is a solutions of the potential V is a function of x, y, z is going to be there. Sorry. And to find out this one, we can think about another configurations. That means in this region of interest, there is a charge is there. That means we are supposed to solve the Poisson's equation, and that Poisson's equation should meet our boundary conditions. That is, at a distance from here to a radius r, everywhere on a spherical surface, the potential should be 0. And the mirror image of this charge, that is q dash, has to be placed inside this region. It cannot be placed outside the regions, so it should be kept only other regions. That means inside the sphere only that should be kept. So here q dash is kept from the center of this sphere at a distance b. And how much the amount of the charge q dash will be there? The amount of charge q dash is equal to minus r upon a into q, and it is a place at a distance b, that is equal to r square upon a, that is known distance. R square is the radius and a is the distance from here to the charge q. So the this q dash is kept from the center at a distance b, that is equal to r square upon a. And the magnitude of the charge q dash is also not going to be identical as q, it is also different, that is equal to minus r upon a into q, that is the magnitude of opposite charge is placed at a distance b. Why it is made like this one? Because then and then only everywhere from this point to a distance r, that means to a radius r, actually there is no conducting plane, but you can think imaginary sphere is going to be there of radius r where the potential is going to be 0. That means it will meet our boundary conditions that at a distance capital R everywhere the potential is going to be 0. So then and then only this potential is equal to potential of this condition is going to be there. Examine the completely different configuration consisting of point charge q together with another charge q dash is equal to minus r upon a into q, placed at a distance b is equal to r square upon a to the right of the center of the sphere as in figure 3.13, no conductor. Now just the 2-point charges. And what will be the potential because of this 2-point charges? Because of these 2-point charges, the potential Vr is equal to 1 upon 4 pi epsilon 0 because of the first charge q upon distance r. What is r? R is the distance from charge q plus q dash upon r dash, that is contributed because of charge q dash. R dash is the distance from q dash to a point P. So this potential can be obtained in this situation where r and r dash are the distances from q and q dash respectively. Now it happens that this potential vanishes at all points on the imaginary sphere of radius capital R and therefore fits the boundary conditions for our original problem, and in exterior there is only one charge plus q at a distance r from the center of sphere. And hence we can give the conclusions that equation 3.70 is the potential of a point charge near a grounded conducting sphere. Notice that B is less than R, so that image charge Q is safely inside the sphere. You cannot put these image charges in the region where you are calculating a potential V. That would change the rho and you would be solving Poisson's equations with a wrong source because the charge will be added. So the charge distribution is going to be changed in both the conditions. That means we are solving the Poisson's equation with wrong source. That's why the image charge should be kept in another regions, not in the same regions. Now the question is this, you might be thinking about the equation 3.15 and 3.16, that how I could find out that image charge magnitude should be equal to r upon a into q and it should be kept at a distance b is equal to r square upon a. This we can actually calculate by another problem, and that I will be discussing here. Here you can see that the same thing is there, but I am changing the notation. So please tolerate me with this one. Let us consider the same kind of problem is here, that there is a sphere of radius capital R, and from this origin or center of the sphere at a distance s, instead of a, here I have changed the notation s, charge q is placed. Now radius of the sphere is capital A, R, that is going to be the same, but image charge q dash is placed inside and the magnitude of this charge q dash is equal to minus r upon s. that we are going to find out. It is kept at a point L on this diameter Mn. Mn is the diameter of the sphere. What is the distance OM? That is the radius. ON, that is also going to be the radius will be there. So we can substitute what is the potential because of this charge and what is the potential because of this charge, that we have to calculate. To find out that one, we have to think about two boundary conditions. One boundary conditions, S is equal to R. That means this distance is going to be R. Everywhere on a conducting plane, the potential is going to be 0. That is one of the boundary conditions. And if we consider that S is very large, this distance with respect to this one is going to be very large, then the potential is going to be 0 or tends to 0. So these are the two conditions for our region of interest, external regions. Now, to find out this one, we will find out the potential at point M and potential at point N due to the second configuration, that is due to the charge Q and charge Q dash. So, what is the potential at point M due to the charge Q? That is equal to K. I will put a K, that is nothing but 1 upon 4 pi epsilon 0, and the K is going to be cancelled out in the ratio. So, in this equations nowhere K is going to be placed, but you understand that V is proportional, potential is proportional to 1 upon R. So, that is equal to V is equal to K upon R. Potential at M due to the charge Q is equal to Vmq, that is equal to Kq upon S minus R. What is S minus R? The distance from Q to a point M. What is that distance? The total distance from the center to the Q is going to be S minus this distance is going to be reduced, that is going to be radius of the sphere. So S minus R is the distance from Q to point M will be there. So that is kept over here. Similarly, potential due to the induced charge Q dash is, sorry, not image induced charge, but it is image charge Q dash is equal to potential at M due to Q dash. Again, that is equal to minus Q dash because it is opposite charge upon R minus A. What is R minus A? It is nothing but again the distance from Q dash to the point M, or LM distance. What is this LM distance? The total distance R minus A, that is the distance from L to M will be there. So that is substituted here. So this will contribute the potential due to the charge Q dash at point M. Now the total potential at point M, that is going to be potential due to the charge Q as well as potential due to the charge Q dash, and taking the summation Q upon S minus R, K is common, so it is cancelled out, minus Q dash upon R minus A, this is equal to 0 because potential on the surface of the sphere is 0 everywhere. So this is one equation we have obtained. Now, so we can compare this one. This equation is equal to Q upon S minus R is equal to Q dash upon R minus A. We are taking the ratio of Q upon Q dash, that is equal to this cross multiplication S minus R upon R minus A will be there. This is your equation number 1. Similarly, we can find out what will the potential at another exterior, that is point N. Again, the total potential is going to be 0. Here also the potential is contributed by Q as well as Q dash. So what is the distance from Q to point N? The distance from Q to point N is equal to this distance S plus R will be there. And due to the another one, that is Q dash to N is equal to this distance radius R plus A will be there. That is going to be substituted here. And potential at N due to the charge Q is equal to Q upon S plus R, K will be there, but that is in a ratio will be cancelled out, that's why I have not mentioned. Similarly, potential due to the charge Q dash is equal to minus Q dash upon A plus R. total potential at point N is equal to Q upon S plus R, that is this, plus Q upon minus Q dash upon A plus R, that is this, and this total potential at point N is going to be 0. And substituting this, we'll find out Q upon Q dash is equal to, again S plus R will be taking here upon A plus R, that is equation number 2. So now you can see that we are having two equations. Equation 1 is also in the form of Q upon Q dash. Equation 2 is also in the form of Q upon Q dash. So equation 1 and equation 2 can be compared. They will be equal. So Q upon Q dash is equal to, we can compare these two equations. Relations between these two, Q upon Q dash is equal to S plus R upon A plus R, this is equation 1, is equal to S minus R minus A, this is the equation 2. So comparing this one and cross multiplication, you can say that S plus R minus A is equal to S minus R into A plus R. And by multiplication and solving this, we are getting the value of A is equal to R square upon A. That means the image charge is kept at a distance from the origin or from the center of the sphere at a distance A is equal to R square upon S. In our original example, it was B is equal to A is nothing but B. B is equal to R square upon A. And substituting this value of A in any one of this equation, either equation 1 or 2, you will find out the value of Q dash, that is equal to minus R upon S into Q. So Q dash upon Q is equal to R upon S and Q dash is equal to R upon S into Q. In that form, you are going to get it. Examine the completely different configurations. That means from the origin, we have kept a charge Q at a distance S and Q dash image charge at a distance A. Now because of that, the potential at this point is equal to, because of this charge, that is K, that is equal to 1 upon 4 pi epsilon 0 Q upon R plus Q dash upon R dash will be there. So this is the potential contributed because of the similar configurations, and that is going to be applied over our original problem, where also the potential is also going to be same. I think we just left about the force. The force between these two, Q dash upon, that means Q1 Q2 upon R square, right? So A minus B whole square. Value of B was substituted here in terms of R square upon A. So then you will get this equation is reduced to this. So force between these two is also going to be calculated for this system or this system, and they are also going to be identical. Thank you very much, friends.